Hello and welcome to the lecture on the financial econometrics. Today we'll be discussing about the volatility model. In the last class we have discussed about two different models of the volatility. That is, we have discussed about the historical volatility model and we have discussed the implied volatility model. And we have seen that both these models have certain limitations. To overcome those limitations, in 1982, Robert F. Engel introduced a model known as ARCH model. Here, ARCH stands for autoregressive conditional heteroscedasticity model. After the introduction of this model in 1982, it has been widely used in economics for the risk management and forecasting the volatility of financial data. So what is ARCH? Before that, let us see why we need the model like ARCH model. To understand that concept, let us revisit the concept of homoscedasticity and heteroscedasticity. You may recall from the previous lectures on the OLS, and let us take an example of a structural model of the kind yt is equal to alpha 0 plus beta 1 x1t plus beta 2 x2t plus beta 3 x3t plus ut, where this ut follows a normal distribution with mean 0 and variance sigma square. So here basically what we are assuming that the variance of this error term ut is sigma square, which is constant, and this assumption we know by the name of homoscedasticity. However, what if this variance is not constant, rather it is time varying? So if this variance is not constant and it is time varying, then what we have, the case of heteroscedasticity. Now, if the variance instead of being constant, it is heteroscedastic, then the estimates of standard errors could be wrong. So if it is wrong, it implies that the inference which we'll be making from these structural models could be misleading. On the other hand, what we have observed in case of financial data, that it often has the characteristics of volatility clustering. Already we have discussed the concept of volatility clustering. Let us quickly revisit here. So what we mean by the volatility clustering is that the larger variance is followed by a larger variance, and smaller variance or the fluctuation is followed by a smaller variance. That is, if we have a large variance at time t minus 1, then at time t also it will be large. However, if it is smaller at time t minus 1, then it will be also smaller at time t. So in such cases, what we can observe, this variance will not be constant, rather than it will be time dependent or time varying. If that is the case, then using such kind of structural model with the assumption of constant variance will not give us an reliable estimate. Moreover, what we have observed, the linear models like ARIMA, which we have discussed earlier. So these models are quite good in capturing the mean dynamics. However, this kind of model fails to capture the variance dynamics. Therefore, we cannot use such kind of model for those series where we have this kind of property. And we know that financial data often has this kind of property. Therefore, we have to use such model which assumes a time varying volatility or time varying variance. How we can formulate such model? What is the idea behind such model? To understand that, let us recall the concept of variance. So we know that for any error term ut, the conditional variance can be given as variance of ut, that is variance of error term, that is the conditional variance here, is conditioned upon the all the informations available at time up to time t, that is it is conditioned upon ut minus 1, ut minus 2, ut minus 3, and so on here. So that means this is the conditional variance of ut. And what is the condition? Condition is that all the informations available up to time t. So this, we know that we can write this variance of ut and ut minus 1 is nothing but equal to expectation of ut minus expectation of ut whole square, that is the deviations of ut square, conditions upon ut minus 1, ut minus 2, ut minus 3, so on. So this is the conditional variance we have. However, we assume that expectation of ut is equal to 0. Therefore, this equation we can write it as expectation of ut square condition upon ut minus 1, ut minus 2, ut minus 3, so on. So this is we have the conditional variance of ut. This structure gives a very interesting information. That information is that the current conditional variance of ut could possibly depend on the squared terms of the past error terms. So this says that the current variance of ut could possibly depends on the squared of past error terms and actually this leads to us to the arch model here. So this structure leads us to the idea of the arch model. So here we can take the angel's opinion that the variance of an standard variance of an error term depends on the square of the past residuals, which could be written in the form of sigma square t as alpha 0 plus alpha 1 ut minus 1 square. So here this is the time varying variance here and it depends on the square of the past residual terms. However, it has been suggested it was better that when we model the both mean and variance equation simultaneously. So often this arch model could be used for modeling simultaneously the mean equation as well as the variance equation. So in that specification, that is simultaneously modeling both mean and variance equation, we could specify this. Let us say we can write RT is equal to mu plus epsilon t, where this RT is the return, let us say here, of the stock prices, say for example, whereas this mu is the constant and this epsilon t is an error term which follows a normal distribution with mean 0, variance ht. This epsilon t follows a normal distribution with mean 0 and variance st. Here st reflects that no more we are assuming that variance is constant. So then this ht we can write as it follows a structure of omega plus beta epsilon t minus 1 square. So let's number it equation 1 and here equation 2. The equation 1 is known as the mean equation, whereas equation 2 is known as the variance equation. And this equation 2 is basically the structure of arch of order 1. So here this omega is the constant which is should be more than 0, whereas beta should be more than or equal to 0, which we call the non-negativity con constraint of the arch model. So what are the key features we have of this arch 1-1 model? So if we look at the structure, the first key feature we can notice here is that it captures the time varying volatility. That is, we do not assume that variance is constant. So here we can say the mean equation through the arch model captures time varying volatility, or time, what we can say, the variance. Second, it captures the very fact which is quite often present in the financial data, that is the volatility clustering. We are able to capture the volatility clustering through the term of sigma t minus 1 square in the variance equation. So it basically it reflects that it captures the fact that when there is the large fluctuation at time t minus 1, that through this particular terms goes to the variance at time t. Similarly, if there is the smaller fluctuation at time t minus 1, it leads to a smaller fluctuation at time t to the ht through this term. To understand this, let us say if we have 2 here, then at t minus 1, then at t it becomes square, that is 4. On the other hand, if the fluctuation is, let us say, half, then at t it becomes half to the power 2, that is 1 upon 4. So if it is larger, there is the further larger. If these are smaller, there is the smaller. So the volatility clustering is very much able to capture through this specification of arch model. Third feature what we have, that this is very simple structure and we can accommodate, we can generalize it to include the different legs. For example, if we can have the arch model of order 2. That means here the variance equation now turns out to be ht omega plus beta 1 epsilon t minus 1 square plus beta 2 epsilon t minus 2 square. Or if we have arch of order 3, we could have ht is equal to omega plus beta 1 epsilon t minus 1 square plus beta 2 epsilon t minus 2 square plus beta 3 epsilon t minus 3 square. Or we could generalize up to order q. So we could write as our q here, so that is ht equal to omega plus beta 1 epsilon t minus 1 square plus beta 2 epsilon t minus 2 square plus beta 3 epsilon t minus 3 square up to beta q epsilon t minus q square, which is the order arch of order Q. However, before implementing this model, we have to make sure whether that series, whether that particular data, does it have the characteristics of arch, what we call examining the presence of arch effect. So let us see how we can examine the presence of arch effect in a particular data. So before using the arch model, we have to examine the presence of arch effect in the series. So to examine the presence of arch effect into the series, we follow a 4-step procedure. So in the first step, what we do, if we have series RT, then we regress it following this particular structure, that is alpha 0 plus beta 1 RT minus 1 plus beta 2 RT minus 2. Depending on the optimum lag, we can go up to the k lag. So let us say here we are restricting as RT minus 3 plus here epsilon t. So once in the first step we regress this, then we get the residuals, that is estimated errors. So we store the residuals here, that is we have the epsilon t hat. So this is not error term, rather than it is residual. Then in the second step, what we do, we regress a equation of the squared residuals on its past lags. Depending on which, the lag is decided based on what is the order of the arch we are going to test. For example, suppose if you are going to test the presence of arch Q effect, that is arch of order Q, then we'll regress the squared of this residual on the Q lags of the its past values, that is epsilon hat square. We regress it on, let us say, theta 0, theta 1, epsilon hat t minus 1 plus theta 2, epsilon hat square minus t minus 2 up second lag, and so on up to lag Q here. Then at the third step, we calculate a test statistics TR square, which is basically nothing but n into R square. The R square here we obtain from the regression we have estimated at the second step, and this n is nothing but the number of observations. And this particular T statistics follows a chi-square distribution of order Q. Then at the fourth stage, we test a hypothesis where we have null hypothesis as that theta 1 is equal to 0 and theta 2 is equal to 0. Similarly, we are assuming and theta q is equal to 0. Where is the alternate hypothesis we have? That is, either theta 1 is not equal to 0 or theta 2 is not equal to 0. Similarly, or theta q is not equal to 0. That means null is that all the coefficient of this regression equation is 0. Whereas alternate hypothesis is that either one of the statistics or more than one is not equal to 0. Then this calculated statistics TR square, if it is more than the critical value or what we call the tabulated value of the chi-square of order Q, is this is more than this, then we reject the null hypothesis. We reject the null hypothesis. So once we reject the null hypothesis, what inference we can make? So rejecting null hypothesis means one or more than one coefficients of this regression equation is not equal to 0. If that is the case, then if inference will make the arch effect is present in that particular series, and using arch model will be appropriate for that particular series. So that's how we decide whether we should use arch or not. So once we use arch, then what are the features we have? So we have already discussed the key features. So overall, we can summarize that once we use the arch effect, it is able to capture the volatility clustering. Second, the volatility is no more constant. So what we are assuming, volatility, that is variance, is time varying. Third, it follows a very simple structure. So fourth, we can have that it ensures the positivity of variance by putting the non-negativity constant on the constants. However, there are the certain drawbacks we have of this model. So what are the drawbacks we have? One of the drawbacks is how we'll decide what is the optimal lag of this arch model. So what will be the value of whether it's of arch of order 1, of arch of order 2, or of arch order of 3. So that is the optimal lag of the arch model. That is the value of Q. However, the one of the solution could be that using the information criteria to find the optimal value of order. Second drawback we have of this is that often it has been observed a large value of the Q, that is a large lags we have to accommodate to better fit the data. So if that is the case, that means a large number of parameters we have to estimate. If that is the case, then often we will be violating the principle of parsimony, that is a smaller number of parameters. Third, in arch we are assuming that the volatility is symmetric, that is both the positive and negative change has the similar effect on the volatility. However, it has been observed that the positive and negative change, they have the different effect on the volatility. So it ignores or not able to capture what we call the leverage effect. The fourth drawback of this arch model what we have is that often the non-negativity constant, so that the variance is always positive, that may be violated. So the sometime this non-negativity constant may be violated. So overall today we have discussed about the arch effect. So there are the certain limitations we have in the we have discussed today we have discussed about the arch model. So we have seen it has certain features, however there is the certain drawbacks we have, and in the next class we'll discuss a different form or extension of this arch, what we call the gauge model, and we'll see how this gauge model will be able to overcome some of the limitations of the arch model. Thank you. See you in the next class.